I'd like to next talk about the topic of conservative forces. Very important topic because conservative forces are the ones which are associated with potential energy functions. Non-conservative forces have no potential energy associated with them. So let's see what the heck these are. A force is considered conservative if and only if both of these conditions apply. One condition, you could use either one as the definition, but one is that the work done by the force on an object moving between any 2 points is the same regardless of path between the points. So in other words, a force is conservative if how much work it takes me to lift this object from there to there is the same whether I go this path from there directly to there or if I go this path from there to there to there. Now, I'm not a conservative force because it actually does takes me more work to get it to there, but gravity is a conservative force. No matter which way I move this from here to there, be it this path, this path, this path, or whatever path I take from here to there, gravity will do the same amount of work. And you can understand that because gravity's only exerting a force this way, so when I move this left or right, gravity does no work. The only time that gravity does work is if I lift it up like this, gravity is doing negative work. If I move it like this, gravity is doing positive work. Theta is 0 for this situation. So the net work that gravity does only depends on where I start and where I end. It doesn't matter what path you take. The other way to look at this is that the work done by the force on an object which moves through any closed loop is equal to 0. In other words, if I start here and move all around, end up right back there, the work done is 0. That's the same thing as the first definition, simply because here's one good path to get from here back to there. Here we go. Go! There's the path I took. I did no work. Gravity did no work as well. Gravity is the conservative force in this situation. If you start and end at the same spot, gravity has done no work. So it doesn't matter if I do this either, same different path, same starting and ending points, gravity again has done no work. So second way to look at it is if you carry something through a closed loop, a conservative force will do 0 work. These are both the same. So let's talk about non-conservative forces, and these are simply forces that do not conform to either of these 2 rules. Non-conservative forces don't conform to rule 1 and 2, and either one is just as good. So let's go ahead and ask which situations, which of these forces rather, are actually conservative or non-conservative, and we'll try to do some demos along the way. So let's start off with the force of gravity. Is that conservative? Well, as we just demonstrated, it doesn't matter which way you move it, which path you take, gravity will do the same amount of work. So that is conservative. I'm going to indicate that with a red check mark if it is conservative. Yes, that is conservative. Doesn't matter what path you take. Between 2 spots, gravity will do the same amount of work. Let's ask now about the force of friction. Is the force of friction conservative? Well, we need an example to figure this out. So here's an example right here. I've got an object A, and I'm going to move it to point B, and I'm going to try to do that via 2 different paths. Path 1, which is just straight line. Path 2 goes around like that, so it's a curvy path. Now the thing about friction is, we're, by the way, looking down on the table, okay? So we're looking down on the table as we see it travel these 2 different paths. Friction will always, if it's on a table, will always oppose the direction of the motion. So the angle between the force that friction exerts and the displacement, if we're dragging along the table, the angle between those 2 vectors will always be 180. So notice if I'm moving it along here, let me switch to this thing right here. If I'm moving it this way, whoops, if I'm moving this along this path, the displacement is to the right, but the force of friction, here's displacement, force of friction, using a different color, will be to the left. Force of friction will be to the left. So it'll do negative work. Well, how about if I take it along this path? Here, the displacement instantaneously, let's just look at that instantaneous displacement. Displacement that way, force of friction, it will be in the opposite direction. So notice that the angle between the force of friction and the displacement of this object is always going to be 180. It's always going to do negative work. But in which case, 1 or 2, will friction do more work, if any? Go ahead and vote on that yourself. Well, if the force of friction is constant, because the normal force isn't changing, the only thing that's going to matter, and the angle between the displacement and force is always 180, the only thing that matters is the displacement itself. Or really the instantaneous displacement. So it's the total of all these infinitesimal displacements. Notice this overall displacement, when you add up all these little vectors, the distance is going to be greater. Now, I don't want to say displacement's greater. The instantaneous displacements, if you added up the magnitudes, would all be greater because this is a farther distance. So in other words, this is going farther with the same amount of force as this. Friction will do more work, and it'll be negative work by path 2. So force of friction is not a conservative force. This is non-conservative. So the next question I have is the force due to a spring a conservative force? So in order to answer that, let's take a look at an example where a spring is exerting some force. So here's a spring right here. And let's say the spring's looking like this. And let's say that right there is the equilibrium point. I'm going to call that x equals 0. That's the unstretched position of the spring. Let me make it a little bit longer. And what's going to happen is I'm going to attach a block to this block, and I'm going to pull this way. So I'll stretch the spring out to this point right there. So there's my mass at the end of this spring. Now, when I release this, my question is this. To be a conservative force, if it starts here and this mass ends right there, if the work done by the spring is 0, in other words, the mass has gone through a closed loop. It started here and it ended there. If that amount of work the spring does is 0, then I have a conservative force. So what's going to happen is the spring is going to pull this way. The force of the spring is going to be this way. Force of the spring. And the displacement is also going to be that way. Delta x will also be that way. So the spring's going to do positive work. Work is positive. Work is greater than 0 for that section of the motion till it reaches its equilibrium point right there. Once it gets to this point, it won't stop because it's got momentum. The spring has to exert some force on it to make it stop, so it will go beyond this point. The displacement will be this way, so I'm going to use blue for displacement. Again, it will go all the way to, let's say, right there. It'll go that way, but during that part of the motion, this spring will exert a force this way. So as you can guess, this part of the motion, the spring will do positive work. This part of the motion right here, the spring will do negative work. Work is less than 0. When you make a graph that shows this, it will look like this. Here is my F versus X axis. F here, displacement X right there. We start off with this spring exerting a positive force while here's 0, so this is negative displacement. So here's what the graph looks like. Looks like that. And this is when it's at its equilibrium point, after which this is what the graph looks like right there. So we can see that for this part right here, we've got positive work done by the spring. And then it's going to actually go, if this is the initial starting point, x initial, x final for the other side will be the same magnitude. So it's for this part of it, it's going to be doing negative work for this part. And the total amount of work it takes for I'm just going to put a dotted line, for the mass to get to a mirror image point where it is, for it to get right, let's say, the same distance away right there from the equilibrium point, that will, I guess my spring's got to be a little bit longer for that to work. Okay. It's going to do a net work of 0 for that, but that's not a complete loop. The net work it does to get it to a spot that is mirror image from over here, that to get it to there, it'll do negative work. But you can easily argue that on the way back, when it's going from right there all the way back, it'll be the exact same graph. So the net work done by the spring is equal to 0 when the object moves through a closed loop. Closed loop is just saying that starting point is the same as the finishing point. That's what a closed loop means. So the work done by the spring is equal to 0. Therefore, we find that the spring is, in fact, a conservative force. Yes, it is conservative. Okay, let's try a couple of other ones. How about the electric force? Is the electric force conservative? Well, we can do the same trick that we did with gravity. Let's say down here there's a positive charge and this object's negatively charged. When I lift this thing up, the force on it, it's attracting, so it's pulling down that way, negative work. But when I lower it back down, it's doing positive work. By the same argument as gravity, yes, the gravitational force right here is a conservative force. Sorry, the electric force is a conservative force. How about the force of a rocket engine? Well, let's take a look at that situation. If I get it, let's use the first definition. Does the force that a rocket engine exerts, will that be this? Does the change in the kinetic energy or the total work done depend on the path? Well, I'm just going to refer back to this diagram right over here. This one right here. A rocket, let's say it's going from point A to point B, will it do different amounts of work if it travels through path 1 as path 2? Well, if we assume that the rocket engine is exerting a constant force, which one of these, 1 or 2, will actually having the rocket engine doing more work? Well, the total distance that it travels right here is greater on path 2. So if a rocket goes from A to B along path 1, it'll be the force of the rocket engine times the length of this. That'll be the work done by the rocket engine. For path 2, it'll be the force the rocket engine works times the length of this path. So it does more work along 2. In other words, if you follow route 2, the rocket will be going faster when it hits point B compared to when you take route 1. So in other words, the rocket engine is a non-conservative force. Go to this color here. Non-conservative, NC. How about a constant force which is in one direction? Will this be conservative? Well, you might think of some common forces that are always in one direction. The force of gravity, for example. Force of gravity is always pulling down. It's a constant magnitude for any mass m. That, you can use the same logic, will always be conservative. Conservative force. And that includes stuff like the force of gravity, a constant force due to a wind, because let's say if the wind is going this way and you're walking into the wind, here's you walking into the wind, moving that way. When you're walking into the wind will be doing negative work. But when you're walking back the other way, the wind will be doing positive work. If you start here and end here, the work done by the wind will be 0. So any constant force in one direction is in fact a conservative force.